at a pivotal moment in the fight against climate change. The world has already exceeded the critical 1.5-degree threshold for global warming, and shifting geopolitical dynamics threaten humanity's ability to achieve emission reduction targets. At Davos, energy and AI have emerged as top priorities, with discussions ranging from AI's potential to green the energy sector to how AI's progress depends on breakthroughs in energy systems. In many ways, we're caught in a paradox. While AI holds promise for optimizing power grids and predicting energy demand and supply, its underlying technologies come with significant energy costs. The International Energy Agency predicts that by 2026, data centers integral to powering AI and other technologies will consume as much electricity as the entire country of Japan. For many countries in Asia, the pathway to clean energy transitions are even more complex, with continued reliance on coal and legacy infrastructure, a rapidly urbanizing economy, and a booming data center industry. How can we ensure that AI adoption is both safe and sustainable, while also fostering equitable energy transitions? Hello and welcome to Code Green, a podcast series where we explore the intersection of climate change and artificial intelligence in Asia. I'm Urvashi Neja, the founder and director of Digital Futures Lab, an India-based research organization that examines the impact of technology on society in the Global South. Through evidence-based research, systematic foresight, and public engagement, we work to realize equitable, safe, and sustainable digital futures for all. This podcast is accompanied by a monthly newsletter where we showcase the latest scientific and socio-technical research at the intersection of AI and climate action. You can access both the podcast and our newsletter at codegreen.asia. Code Green is supported by Earth Venture Foundation, a not-for-profit initiative that supports scientific research to advance climate action. In today's episode, we are joined by John Cotton and Priya Donti. John is a senior program manager at the Southeast Asia Energy Transition Partnership, which supports governments in the region to transition to clean energy. Priya is assistant professor at MIT Department of Electrical Engineering and Computer Science, as well as the co-founder of Climate Change AI, a global nonprofit initiative to catalyze impactful work in machine learning and climate action. In this episode, we discussed how governments in the region are enthusiastic about the use of AI to improve the efficiency of energy systems and manage energy demand and supply. We also discussed the potential of AI in helping integrate renewable energy resources into the grid, something that is particularly important given the uncertainty of variance in renewable energy sources. We also discussed the challenges. Data is sensitive and governments are reluctant to share this data. Moreover, it's a new area for policymakers and decision-making is necessarily slow. Finally, we discussed the environmental impacts of AI and how this can be managed in the Asian region. John made an interesting point that the global corporate demand for clean energy was actually a driver for governments in the region to create greener infrastructure. One of the main things I took away from this podcast was the need to rethink how we approach AI adoption and efficiency gains. Instead of prioritizing resource-intensive, data-centric models, we need to shift towards physics-based, fit-for-purpose models that are more efficient and less resource-demanding. We conclude with a call to action. Investments must focus on capacity building, developing skills to create and deploy AI, as well as developing evaluation metrics to assess and monitor the impact of AI. Let's jump right in and hear from John and Priya. Priya, John, thank you so much for joining us for this episode of Code Green. I'm really excited to have this conversation with both of you on a topic that is extremely timely and I think is on top of mind for kind of policymakers, innovators, civil society folks across the Asian continent. John, maybe I can start with you. So one of the largest sources of emissions in Asia is the energy sector, and as a result of which national governments in the region have been strategizing phasing out coal plants and the reliance on fossil fuels. But obviously, this is quite a complex process. And so based on your work at the Southeast Asia Energy Transition Partnership, what is your perspective on just energy transitions and climate change in the Asian context? Sorry, I know that's a very big question. We'll start big and then we'll drill down from there.
Sure. So firstly, thank you for having me today. It's an honor to be here. And that's a very big question you've started with. So maybe just by way of a very quick introduction, the Energy Transition Partnership is a program managed by UNOPS, and it's our role we're mandated to support the governments of Vietnam, Indonesia, and Philippines with the energy transition. So with that context, when I first joined in 2020, the discussion of coal phase down was off the table. So in fact, in our strategy, we don't have coal phase out in our current written strategy, which is quite unbelievable for an energy transition organization, but it was so far from a possible reality. The climate commitments made at COP26 were very pivotal. So 2 of the 3 countries made net zero pledges, so Vietnam and Indonesia, and the Philippines announced its coal moratorium. So with that change in climate, it really brought coal phase down or coal phase out into the discussion. So as a general view on where the energy transitions are in certainly the countries where I work, we're in a very positive place. There's a lot of momentum. Our role is to design technical assistance for and with the government. When we first started out, it felt like we were working a little bit in advocacy. We were seeking areas where we could be of use. Now, we can't keep up with the demand for the questions which are coming to us from policymakers. We bring in experts to support policymakers make evidence-based decisions on the energy transition. The energy transition is complex. It's very difficult. Technically, we know the solutions globally, but how to apply them in the local context. We're talking about completely redesigning the energy system from something which works very well with a central large power plant feeding a load center to redesigning that. Economically, we know that renewables can and often are cheaper than conventional energy sources, but the market mechanisms aren't lined up to facilitate that. Socially, we're looking at complete changes in society and the main roles that our society is built upon, and politically, both in terms of policy and the vested interest of the current incumbency, we have to overcome this. So we're in the right direction, but there's a lot of work to do, if I summarize.
Thank you. And I think that was a really great summary, and you covered a lot of points. And it's quite interesting also the transition that you pointed to in terms of when kind of coal came on the agenda. So with the governments that you're working with and with the governments that you're supporting, and you're talking about that you get a lot of demand from governments, do they also see kind of digital technologies, technological innovation, AI as playing a role in this? And if so, what kind of role does government see with regard to energy transitions?
Yes, so it's certainly emerging and emerging at speed. Actually, just today I received from PLN, the electricity systems operator in Indonesia, their plans for the digitalization of the energy sector, and they're calling it moonshot. So it's a big, ambitious plan to bring digitalization right the way across the energy sector. Vietnam in 2018 had that year they installed more solar capacity than anywhere else in the world. So maybe don't quote me on that, but I think that's true. Which was a great positive for the energy transition, but it led to problems with curtailment and really emphasized the need of smart grid and digitalization and planning. So Vietnam have since then been exploring digital technologies. And in the Philippines, there's a strong interest. So in the Philippines, there's energy security really is at the top of the energy challenges. And demand-side management as one kind of energy efficiency measure is being explored. And to have successful demand-side management, mapping the demands against the generators is critical in reducing the amount of installed capacity that needs to be there. And the solutions to this are digital. So right now, actually, ETP is working with the Department of Energy on developing its demand-side management policy, which will open the door for all of the AI and machine learning tools which are needed to develop such. So it's in relatively early stages, but I think also globally is. We're talking about a new technology here, and all 3 government from the seat I sit in, I don't like to speak on behalf of the government, from the seat I'm sitting in, are very interested to really leverage the benefits that AI has to offer and empower and capacitated people to be able to take part in this new and emerging economy.
Thanks, John. And Priya, maybe I could turn to you now. You've been leading some amazing research at the intersection of climate change and AI, and a lot of your work has been around machine learning and electricity systems. So, what John was talking about. So what motivated your work in this space, and what is the kind of problem statement that you see that requires urgent attention and that you're working on?
Yeah. So first of all, again, thanks for having me on the podcast. Very excited for this conversation. So what got me into this area? I mean, in short, kind of starting in high school, I knew that I wanted to work on climate change. You know, one of the biggest issues of our time, huge equity related implications. And then in undergraduate, I got interested in computer science. And at the time, this was really confusing to me because it wasn't at all clear how these two things had anything to do with each other. And I was lucky to stumble upon some work from some researchers at the University of Southampton, basically arguing that AI and machine learning would be really critical for the transition to a renewables centric grid. And so here, the problem that we're solving for is that power grids have to maintain this exact balance at every moment in time between the amount of power that's supplied and injected into the power grid and the amount of power that's being consumed. And this has always required dealing with some level of uncertainty because, for example, we don't ask consumers to declare exactly how much power they'll use ahead of time. We have to predict how much that is and kind of balance the grid in the face of that uncertainty. But as we start to kind of incorporate more, low carbon renewable energy that is time varying, so things like solar and wind that vary based on the availability of sun and wind, then we also have to deal with uncertainty on the supply side. And so now we are managing the power grid in a way that we have to maintain this balance, even though it's harder with this uncertainty. We also tend to then say to manage the uncertainty, we're going to have more batteries, we're going to have more demand flexibility and demand response. And so this increases also the number of devices that we're optimizing over. And this increases the scale then of the problem that we're addressing. So the question that in some sense we're asking is, how do we manage with greater speed and scale these power grids with large amounts of renewables? And this is where AI and machine learning tools can potentially be helpful alongside kind of other advanced optimization and control techniques.
Thanks, Priya. And in the kind of larger scheme of when we're talking about climate change and climate solutions, how important do you think this piece is in terms of kind of moving the needle on climate action?
So, in general, the idea of having power grids that can kind of accommodate large amounts of renewables in many countries, right? The kind of strategies to decarbonize not just the power sector, but energy systems more broadly. So, let's say like buildings, transportation, energy related sectors are kind of relying on the ability to electrify and actually kind of draw clean energy from the power grid. And so, in some sense, the power grid serves as a backbone for a lot of energy transition strategies. And as a result, this piece of how do you actually integrate it all together and get that to work is extremely critical. The other thing that I didn't mention earlier is this idea that it's not just about operating the power grid that you currently have, it's also about planning for the future and planning a power grid that can accommodate the changing loads and also the changing climate, right? The places, for example, that are windy today are not necessarily the places that are windy tomorrow. And so we actually have to accommodate that as well. And so this really requires us to actually to plan in a more intelligent way. And I think there's a lot of work to kind of better assess what future scenarios for energy demand and energy supply might look like, and to kind of run both technical and policy related planning processes more effectively in order to deal with that.
Right. And let's say we assume, and which is, I guess, exactly the problem that you're working on, that we do crack this from a kind of technical end. We figure out the right algorithmic systems that we need. We figure out what that optimization looks like. What are the other pieces of the kind of enabling ecosystem that one might need to actually be able to realize the full potential of some of the ML solutions that you're talking about? Whether it's infrastructure or maybe the quality of the power grid, maybe it's the technical capacity to run it, just to get a sense of, what else is required.
Absolutely. And I think you hit on some of these very important aspects, right? So, first of all, to manage a power grid, you actually have to have a good power grid. So, there has to be good physical infrastructure and good digital infrastructure. There has to be good kind of human capacity in order to actually understand what's going on, in order to be able to manage the system, alongside kind of technical algorithms, for example, that are running some of the lower level pieces more automatically. Um, and for the planning processes, I think there has to be kind of ability to engage with the public and key stakeholders in order to understand what the needs are, both from kind of a macro perspective and more granularly, for example, from an energy justice perspective, in order to understand who is or isn't being served by current modes of operation. So, for example, when we plan power grids, we're often planning for certain metrics of reliability, trying to make sure that consumers, for example, don't lose load in the US for more than a certain number of minutes or hours per year or several years. And while these metrics are often looked at in an aggregated way, so what is the average consumer facing in terms of reliability? Often when you look at this in a more disaggregated way, you see that some consumers are losing powers 10 or even 100 times more than others. So I think really kind of figuring out ways to incorporate some of these distributional considerations into the way we plan, that kind of public consensus building and public stakeholder engagement becomes really important.
Thanks, Priya. And John, maybe I could turn to you and ask you to reflect a little bit on what Priya was talking about in terms of, so we have the potential of optimizing power grids, of optimizing the use of renewables, integrating that into our existing power grid. But at the same time, like Priya was mentioning, we do need all these other kind of building blocks as well, and the other parts to this kind of ecosystem. And of course, we also need the kind of natural resources to even have that renewable pool in the first place. So could you talk a little bit about where we are in the Asian context and what you see are the opportunities of the kind of AI application that Priya is talking about?
Yeah, so it's very easy to follow on from what Priya said, because she's talking right at the heart of the main challenge and really the heart of the energy transition. The grid is right at the center of all of the challenges that we face and all of the opportunities. So I couldn't agree more with you, Priya. When we first went into Indonesia, so I'll use Indonesia as a case study here. When we went into Indonesia, at that time, Indonesia had not so strong climate commitments, certainly no coal phase down, and not very high ambitious targets on renewable energy and especially variable renewable energy integration. And when discussing with policymakers and the utilities, primary reason they gave that they can't move forward with this is that the grid isn't ready. That simply they cannot incorporate variable renewable energy into the grid. At the heart of that is a control center. So ETP's first work in Indonesia was to design a new control center for the Java Bali grid, called Jamali grid. This control center feeds electricity to circa 160 million people. It was already antiquated, and it still is at the minute, far from smart. So bringing in a new SCADA EMS system, the electrical control center with smart technologies allows the operators to start considering the incorporation of VRE. So taking a sympathetic approach to the utility, their primary task is to deliver secure, reliable power to their consumers. And if they don't, they fail at their job. The control center is a very high pressure, high stress environment. As Priya mentioned, this matching of load and demand it's live, and it's predictable to an extent. And under the current system of having large coal plants feeding into a capital city, for example, you can roughly turn it up and down, turn it on and off to match the ebbs and peaks of the day. You throw on top of that wind and solar, which is when it's windy we have it, and when it's not we don't, and when it's sunny we have it, and etc. It becomes very difficult. So from a practitioner's point of view, that's a nightmare. It's like an air traffic control center inside one of these control centers. So without bringing in modern technologies, it's almost an impossible task to get the load correct, to get the generation meeting the load, and to balance it across the system. So I'm just to share anecdotally, because everything I'm saying you can read in reports, but what also, like yourself, Priya, I'm from a pure science background. My first job was in help desk, and the worst day of the year you could have in help desk was when, for example, Windows XP changed to Windows 7, or when there's a new version of Word. Everyone in the office has a meltdown. Nobody likes change in IT systems. So we had a huge fear that trying to roll out such a new technology with people who are very good at their job and delivering electricity as they plan to, why would they want to embrace this? Why would they want such a change? And yeah, there was resistance at the beginning, but the further we got along the project and the more they learned it to do, I remember as we came to the end of the project, there was just sheer excitement, the new toys that were there to play with, and questions that started coming to us from both the practitioners in PLN and the ministries is like, okay, how can we get some VRE in the grid to start playing with this? So inadvertently, we went from a situation where it was complete bottleneck, we could not get past this blockade, to a genuine desire for A, for climate, B, for new technologies, but C, just because they can, and that's, they have the toys and the tools to do so. So that's answering your question, kind of a Indonesian perspective, but similar stories exist in Philippines and Vietnam, where they're really embracing these technologies and want to push forward. And I think we might have a chance to talk later about these. Thanks.
So when you're introducing something like this, when you're introducing an ML system to improve the optimization of the power grid, but this is also like a power grid, like you're saying, that controls a whole city, right? That, I mean, it's the infrastructure, the basic infrastructure of the whole city. So do you have to kind of phase this? Do you introduce it in like a sandbox testing kind of environment, or can you just go straight in, or is there some in between where you introduce it in pockets but not entirely? I'm just wondering like what that transition actually looks like.
Yeah, so in the case of this particular example, it's phased. So the new system will, so first of all, right now the control center is under construction and the teams are, we're building a physical control center as well as the software. So all of the teams are under training and using it in sandboxes, as you say. And when it's launched, it will look very much like the old system looked like and work very much like the old system. And then there's a transition into, there's a lot of toys and tools that can be turned on, and these will be done gradually. It wouldn't be prudent to make that transition quickly. That's at the control center, which is the biggest piece. But simultaneously, going hand in hand with this, we're looking at smart substations. We need to install all types of monitoring system across the grid, and it will build up over a series of years. We designed a smart grid roadmap for Philippines and Vietnam, or we supported the governments in developing their smart grids roadmap. And what I learned from that, talking to consultants working on it, was there's not really such a thing as a smart grid. This isn't something that's designed and out of the box. There are multiple solutions for multiple challenges, of which the solutions can and will be smart in certain scenarios. So we're not talking about a complete overhaul of the system as it is, but a gradual set of solutions applied to a particular context.
Got it. And Priya, maybe that's a nice segue into my next question to you, which was, that obviously the intersection of AI and energy is complex and there's many layers to the energy sector. So can you break down some more of the use cases that you see of AI for the sector?
Absolutely. And so one thing to kind of understand about AI is that AI is actually an umbrella term for a kind of very diverse and wide set of techniques. For example, there are two big categories of AI, one of which is rule-based systems. You know the rules of the game, for example, the game of chess. You write them down and you have an algorithm learn how to reason over those to become a good chess player. And the other branch, the predominant branch today, is machine learning, which is used in situations where it's actually hard to write down rules. So, for example, if I have a bunch of images of dogs and cats, it's hard to write down a set of rules that tells me exactly why each image is a dog or a cat. But intuitively, as a human, for example, we can look at an image and know, is it a dog or a cat? And so in that situation, what we're asking a machine learning algorithm to do is given a bunch of examples to try to learn the patterns within the data that are causing that to be the case. And so given this idea, kind of, a lot of these applications are of machine learning, which is identifying patterns in data. There are actually a lot of ways that plays out in the energy sector that are quite interesting. For example, machine learning can be used to distill raw data like satellite imagery or physical signal data into actionable insights that can be used for operations and planning. So, for example, there are several efforts that try to take satellite imagery and kind of use that to figure out, okay, if we don't know where all the solar panels are, where are they? If we don't know exactly the locations of the transmission or distribution infrastructure, where is it? If we don't know exactly where emissions are coming from at the entity level, where are they coming from? And this requires a combination of, again, this raw data alongside insights in terms of how do we label that data, how do we combine it with other data, but given that the machine learning algorithm is learning patterns that are allowing to make these identifications. Another example where machine learning is used pretty widely is nowcasting or near-term forecasting. So, for example, can we figure out or predict how much solar power there's going to be produced on the grid, or how much electricity demand there will be on the grid in the next few minutes or hours, by taking in information like weather predictions, like historical data on how solar power production or demand looked, or even aerial imagery telling us how clouds are moving overhead, feed that into a machine learning algorithm and have it identify patterns to figure out when the data looks a certain way, what does that imply in terms of what the solar power production will look like? Both of these are kind of decision support applications, but they're also places where machine learning can actually help to automatically optimize or control different devices in energy systems in order to allow us to actually hit this balance between supply and demand. So, for example, the French grid operator RTE put out a challenge over several years called the Learning to Run a Power Network Challenge, which explored the use of a particular set of machine learning technologies called reinforcement learning to actually figure out how to adjust the power generation of different power generators, as well as switch various kind of lines and other components on the power grid in order to actually reduce congestion and reduce costs in the face of also uncertain events. John mentioned demand side management earlier. This is another example of where machine learning can help to kind of intelligently control, for example, heating and cooling systems in buildings, or kind of industrial freezers, or batteries also, or other kind of devices that can shift their electricity consumption or charge and discharge, and do this in a more kind of scalable way. On the planning side, we talked earlier about how kind of more effectively planning power grids in the face of more uncertain scenarios and greater scale is going to be important. And planning models are large scale kind of physical or optimization models that are really computationally intensive to run. And so there's been some amount of work trying to actually approximate all or parts of these models using machine learning, basically treat a part of a model like you're putting in an input, you're getting an output, get machine learning to learn a fast surrogate model, proxy model for that, that allows the overall planning model to run faster. And then kind of there are some really interesting applications also in accelerated science. So can we, when we're trying to create a better battery, we're trying to create better electrofuels, this process requires actually figuring out, okay, I'm going to try to synthesize a particular battery. I'm going to synthesize it. It's going to take several months to actually then test it. And then I have to go back to the lab and design another battery. Can we speed up that process by learning from the outcomes of past experiments and recommending which experiments to try next in order to cut down the number of design cycles that are necessary to create that next battery? So this is only a small set of examples, but I think basically there are lots of ways that machine learning can really play a role in decision support and automated optimization and control, in planning and in kind of accelerated science. And in all of these cases, though, it's important to recognize that machine learning is not the end-to-end solution. It is a piece of the broader solution. And so really important to think about both from a technical perspective. That means that there are certain requirements on these models. So for example, in certain cases, you might need interpretability if you need to explain decisions to a regulator should something go wrong. You may need safety if you're really talking about safety critical physical operations. So there are kind of technical requirements that leads to, and also kind of socio-technical requirements in terms of things like how do you start to integrate this into software? How do you provide this decision support to people that become really interesting to consider?
Thanks, Priya, and thanks for that overview. And I really appreciate also you breaking down the kind of, that AI is also an umbrella term, and there are these different forms of AI, and what we're talking about right now is machine learning systems. I guess the follow-up question that I had is that given the reliance of machine learning systems, or given that, data is the crucial ingredients of machine learning systems, and you do have kind of pockets of data scarcity or uneven kind of data access and data quality across the globe, how does that play into the kind of real world usability of some of these systems in context, like Asia, for an example? And just as a kind of follow up to that, is that, how plug and play are these systems, right? Can you just like take an off the shelf system, AI ML system for something like nowcasting and be able to apply it somewhere else? So then is there a kind of extensive process of fine tuning that using local data and then requiring kind of, I don't know, local domain expertise to kind of build in that almost like an expert system to support how that machine learning system runs?
Yeah, this is a great question. And I will say data is important. So kind of since given that machine learning algorithms are basically learning patterns in data, if there is no data or there's very poor data, then machine learning systems are not going to work well. In terms of how we address this, there are two, I would say, kind of prevailing philosophies at the moment. So one of these philosophies says, well, let's create general purpose models in places where data is abundant, and then kind of fine tune these models with smaller amounts of data in places where that data is not abundant, but maybe there are kind of insights that transfer from one setting to another. So, for example, if we're learning to kind of control a power grid in the US and we have a lot of data about that particular power grid, then can we create a model that does that in the US context and then fine tune it with information from the Asian context in order to transfer it over? So that's one philosophy. Another philosophy basically says we actually really want to be building kind of regional specific, location specific, context specific models that are really contending with what is the data availability that we have, what are the unique nuances of the situation, and build models that are fit for purpose in that way. So, for example, in situations where we don't have a lot of data, but maybe we do have physical understanding of what's going on in the power grid or existing process knowledge, can we create physics-informed machine learning models that are actually incorporating inherently knowledge of the existing physics and are learning the rest from data, but now you need much less data than if you were trying to learn those physics from scratch. I think it's important to understand that these two kind of philosophies exist, because I think often in the mainstream, there's this perception that, okay, the only way or the best way to build machine learning models is by collecting and gathering infinite amounts of data, and kind of creating very large general purpose models, and implementing them. But actually, right, depending on the particular setting that we're looking at, this comes with different trade-offs in terms of, again, kind of how much you're investing in actually collecting and creating data, how much you really do believe that insights transfer out of the box from one place to another. I think in practice, honestly, they don't, and that you actually have to do a lot of on-the-ground work to understand specifically what's going on in a particular context and how to construct your models for that particular context. And also implications in terms of who is able to create and maintain and audit these models. I think kind of the paradigm of general purpose models often implies that there's more centralization or particular entities that are shaping these models over time, whereas the paradigm of more domain or context specific models implies that different entities have the kind of ownership and ability to shape how those models look in the longer term, because they are more tuned to the local context and can be adapted more readily for the local context without reference to how some other general purpose model is being updated. So in some ways, this question is actually, it's both a technical question and a socio-technical question. And I think it's really important that there's recognition that when we're deciding how we actually shape and develop AI technologies, that we're actually making implicitly a lot of decisions in terms of our investment in who's investing in data, who's actually having the ability to own and shape these models, and that we really take that into account.
Thanks, Priya. And this is the second time on this podcast series that someone's brought up the idea of physics-based machine learning, which makes me really happy because, otherwise when we talk about machine learning, there's in the kind of dominant discourse, there's typically a singular kind of imagination of it. But John, maybe to kind of to pick up on what Priya said on the point around kind of data availability, data quality, but also this idea that you really do need that kind of domain expertise or expertise that is rooted in that particular context. So where would what is the kind of level of readiness that you see in the countries that you're working in? And are there similar kind of use cases that you see around AI that folks are exploring in the countries that you work in?
Yeah, it's difficult. There's a huge amount of capacity building that needs to take place. That's not just in this region. That's globally. We're dealing with new technologies. At the heart of being able to use AI and machine learning, as Priya said, we need data. In most cases, moreover, we need quality data. The governments will develop policy based on data generally outside of machine learning. And the more data we have, the more quality of the data, the better the evidence we have for the evidence-based decision-making. That requires investment. So when we're looking at the grids and the grid infrastructure, that requires investment. And the question of who and where this investment comes from is the first part of the discussion. The second part is who and how do we use this data? So if I maybe take Vietnam as a case study, there's a big discussion around the access to data. We're not talking open source here. It's very sensitive. So who and how the data is collected, used, and then accessed is the first barrier the policymaker faces. So whilst we might have somebody like Priya and an organization willing to come to work with government, we're talking about geopolitical sensitivities. So it's difficult for the policymaker to grant access. So we have to work a lot on theoretical level and with sample data sets. That, of course, then limits the reality and application of the models that are being developed. That's perhaps a Vietnam lens. In Indonesia, we have a PLN, which is the energy market is dominated by this state-owned company. So any AI model needs to fit inside the highly structured policy and regulations that exist within PLN. And PLN is a huge, huge organization with so many layers to go through. So to reach the kind of decision-making level will take a long time. And again, comes back down to the question of who will invest in this, why will they invest in this, and for what long-term reason. And to do that, you need to have a clear vision of where the sector is going. And this takes time to break down. This takes time to come from the presidential or prime minister's office through like the NDC process to set these commitments to attract investment. Indonesia and Vietnam both have strongly state-owned electricity sectors. Where in the Philippines, it's private sector driven. So then the question isn't who will invest. It's how do we attract the private sector to invest, and how do they make a return on this investment? At what juncture of the energy system, which currently doesn't exist, can these AI tools, machine learning tools, be attractive to attract private investment into the system? I think demand side management is an easy one to visualize this. So by bringing in demand side management tools, you can work with the multitude of entities in the space and make them all more profitable. Basically, you're saving people money, you're optimizing systems, you're bringing efficiency across systems, but it's a long-term play. It's not a quick return on your book. So it requires a policy framework that gives you the time and space to bring these investments into the country. So yeah, the policy development to allow such to happen is now under discussion. But as it's new to this region, but also globally relatively new field, it's a difficult area for policymakers to make strong statements and commitments, because I'm working in this field for the last 20 years and it's new for me, and I'm coming to terms with how and what is happening, and it's transitioning so quickly. So for the policymakers to sift out what is and what isn't applicable to their particular country, their particular situation, I think is the first challenge. So workshopping, capacity building, exposure is very, very critical to understand just what can be applied out of the box, what needs to be developed in country, and what needs to remain under strict state control, because it's deemed highly sensitive information. There's some of the challenges we have when we discuss about opening up for the collection of data sets and then the application of AI and machine learning.
Thanks, John. So recently in its Energy Outlook, the IEA projected that data centers will account for almost 10% of global electricity demand. So how is this conversation on AI's energy consumption and the potential impact on grid and access to electricity shaping policy conversations in Asia? What is the policy conversation you're hearing in Asia?
Yeah, it's huge. There's a big question there focused around the specific energy consumption from AI. But if I can answer it a little bit more broadly on the global corporate demand for clean and green energy, of which AI is a big driver of this. So we talk about Amazons and Googles. They already have, and they're looking at building a data centers in this region. To build a data center in this region, they're demanding access to clean energy, and it's not there. So the grids of Philippines, Vietnam, and Indonesia, it's not there. So, and there's many mechanisms we can use. Renewable energy certificates, for example, trading for various RE sources. Of course, the ultimate approach is greening of the grid, wholesale greening of the grid. But these companies will make multi-billion-dollar investments into a country, and there's a competition taking place between the governments, the countries of ASEAN, to attract this large level of investment into the countries. So in Indonesia, we're currently doing a study called the opportunity loss of the energy transition, meaning we're looking at opportunity loss. So which companies have considered Indonesia to invest in but haven't because of their lack of availability to invest, to procure clean energy. That is that is a great driver. It's a great driver for the space and the policymakers. So we're seeing, partly as a result of this, energy efficiency standards are improving, increasing, and rising. So government setting guidelines for the data centers to adopt renewable energy or improve efficiency. Grid resilience planning is all part of this. How do we attract these data centers to our data centers being one of them? How do we attract them to our country? And then what public-private partnership policy mechanisms can be introduced so that we can create, for example, net zero industrial parks. So both Vietnam and Indonesia are very progressive in developing net zero industrial parks so that they can attract this type of investment and feed this green energy. So it really is. I remember looking at these maybe 10, 15 years ago, RE100 companies, wondering if the producer, the manufacturer could have an impact on energy in the region. Slightly anecdotal. When I worked in Laos, the shoe and clothing manufacturers in Cambodia wrote a letter to the country's leadership saying that if X number of coal plants went ahead, one was going to come across from Laos, they would leave. They would leave because they can't anymore fulfill their obligations under their own net zero policies. And it resulted in Cambodia taking a very aggressive approach and went ahead and built a massive solar project. Of course, it was more than this, but at a simple level, that was based on one letter of industries coming together. So that the power of the AI industry, of the data centers, of large corporates demanding green energy, is the effects of it are very tangible, and they're part of the discussion, a large part of the discussion.
I think that's fascinating, John. That's something I hadn't thought of earlier about, the kind of demand for clean energy by these global tech companies or global corporate players, and what that might mean for that, how that might be a driver for policy change. I was just wondering, so this global corporate demand for clean energy, and as they're making investments in Southeast Asia, where does that demand come from? Is that demand because they feel that it's going to be good for business? So is that demand also from kind of the regulatory and jurisdiction that they operate in, or where they're headquartered? I'm just wondering, like, how stable or fickle is that demand?
So I've asked this question several times. I think a cynical view is it's good for business. Consumers maybe it's not cynical. Consumers demand it. Their own customers are demanding this. It is one driver. That's for business. The answer that I normally get is that the corporates have an ethical stance on this. They're genuinely concerned about the impacts of climate change and see their corporate social responsibility as imperative to drive this forward. That's the answer. And I get when I ask these questions. I think there's a whole host of other drivers underneath it. But whatever the driver, it's a good thing and it's working. So if you take a bottom-up approach, it shows that at the advocacy level within countries, consumers and groups of people coming together to demand that their product, whatever that might be it an internet service or be it an item of clothing, has an ethical supply chain. And in this terms, I guess I'm using ethical in terms of low carbon footprint, only one of the ethical considerations. But as long as people are demanding it, so this bottom-up approach seems to be working. The top-down approach is the finances. So many of the banks, as you know, are increasing their demands that before they loan money, that the organizations must meet certain CSR requirements, one of which is the carbon content of a product. And then, of course, sitting on top of that are the countries where they're from, having their own net zero targets under the COP process, the UNFCCC processes. So I think it's really a combination of bottom-up, top-down, and it would make a fascinating thesis or postdoc actually understanding the percentage implication of each one of them and where the best lever is for us to be pulling to drive this forward even faster and further.
And how we sustain that lever for change. Priya, you've also done some work around the social and environmental sustainability of AI solutions, and how the kind of narrow focus on efficiency gains of generative AI overlooks its kind of sustainability impacts. Tell us a little bit more about that work and the issues that you think that need to be addressed. And, just more broadly, I think even in the past couple of years, the discourse around the climate impacts of AI, whether it's, in terms of energy consumption, etc., have become kind of mainstream. We see, mainstream newspaper publications covering it. And at the same time, we also see some of the big tech companies now, reopening nuclear plants, for an example, to be able to sustain their energy needs. And that kind of option is obviously not available in these parts of Asia. So would love to know a little bit of your thoughts on the kind of environmental sustainability of generative AI and AI more broadly, if you'd like to reflect on that.
Absolutely. So in some sense, you said like there's some narrow focus on efficiency gains of AI. I think even stepping back, there are some pockets that are not even focusing on efficiency gains, right? Are saying it doesn't matter how much we consume, we can just green the grid. And as you've pointed out, we can't, for example, green the grid literally everywhere. When we put renewable or clean energy on, kind of AI is not the only user of that. So we have to think about, how do we jointly kind of green all loads, not sort of kind of attribute or kind of let sort of AI claim that it is the kind of user procurer of that green energy. And also we have to think about, the fact that kind of, growing electricity usage more broadly, it's inconsistent with kind of energy sector decarbonization pathways, which require efficiency, which require some amount of leveling or even fall off of electricity use, and ignores things like the fact that data centers also have, water impacts are often cited in water scarce regions, that they often will kind of have implications for electricity pricing for nearby consumers. They're created they require minerals and materials to create. So I think that there's definitely, right, like a need to kind of, not just green the grid, but do all of these other things, including making these technologies more efficient. But then, okay, so let's say the framing is use generative AI for everything, but let's make it more efficient. one fallacy in that argument, first of all, is, where AI is useful, not all AI is generative AI. And generative AI or large foundation models, they're not necessarily the right tool everywhere, even where AI is well suited. I think sometimes the narrative of make generative AI more efficient, which again, efficiency is a very important lever, but sometimes the way it's framed is used to imply that there's no other choice. And as we talked about earlier, right, when you're using, for example, foundation models versus physics informed models, you're making implicitly different choices about how much data or computation is needed. There's a whole movement in tiny ML and tiny machine learning, which is also important if you're deploying things on hardware. And so just assuming that we'll use generative AI for everything and just making it more efficient kind of misses the point. It's also thinking about what is actually fit for purpose, what are the resource and other kind of agency, other trade-offs behind it, and how do we do that? And then, of course, like more broadly, when we're thinking about the climate impacts of a technology, we need to not just think about its inputs, so what were the resources that were used to create it, but its outputs, which is to say, what are we actually using the AI or generative AI for? Ideally, we would be using AI for good things, like AI for climate action, and we should do so in a way that is good. So kind of, as little resource consumption as possible in a way that is responsible and ethical. But importantly, we also shouldn't use AI for bad things. AI is actively being used to accelerate oil and gas exploration and extraction. It's a driver of kind of how information spreads online. And that in many cases means that when you have algorithms optimizing for engagement, then that's often optimizing for incendiary content or misinformation. And there are other places where, applications of AI may not kind of out of the box be good or bad, but we actually have choices in terms of how we shape those applications to be climate aligned. For example, AI is a key technology behind autonomous vehicles, and if we can develop the autonomous vehicle sector in a way that either is increasing the emissions of the transportation sector by prioritizing kind of private fossil fueled kind of existing modes of transit, locking us into roadways, or we could actually use it to help us transition to a maybe much more low carbon, multimodal, public, form of transportation by making it much easier to connect between different modes of transit. As we have actually choices in terms of how we apply AI, in terms of whether in that case it's going to be an asset towards the energy transition or not. And so basically right now, I would argue that in the media, the kind of headline that often comes up is AI could help us solve climate change if it doesn't kill us first because of its direct impacts. And I think that basically oversimplifies the story, which is that we need to think more broadly about AI's uses across all applications. So where AI is being used for good, bad, neutral, other, kind of make sure that we're aligning our uses of AI with climate action, making sure that we're not wastefully using, that we're not kind of, working on applications that are counterproductive, and that we're shaping applications that we are doing in ways that are climate aligned. And then for those applications that are worth it, then make the back end as efficient as possible. But sort of, it's not kind of assume that we will use it everywhere and make it efficient. Instead, let's be thoughtful also about where we're using AI.
Thanks, Priya. And thanks for also weaving in so many different critical elements or parts of the conversation into that reply. And I think, it really, for me, underlines the idea that sometimes like a very use case approach to thinking about AI and climate or AI in any other social sector is quite limited, right? We need to kind of think of it as a much broader kind of system approach where what is the broader theory of change that we need for XYZ sector, and where really can AI fit into that, and what might be some of the other the unintended consequences or the second and third order consequences, and really take that kind of system view. So thank you for joining the dots on many of those pieces. We're almost at time, so maybe just a last question to both of you. One of the main audiences for this podcast, or who we're trying to influence, or trying to inform thinking, is the funding community, whether it's global philanthropy or domestic philanthropy, or kind of private investors in the climate tech space. So given where you both sit, what would be your recommendations or call to action for that, for the funder community?
So I think if let's rewind 50 years, 70 years, um, and look at the society we're sitting in now and the problem that we have with climate change. It seems insurmountable. It's a huge problem. It's really multidisciplinary. Every single policy area that we at ETP are involved in, we're very aware it has knock-on effects right the way across society. So, for example, we can try to support a subsidy decrease for coal, like take subsidies off coal. That's critical. But the knock-on effect it has across all areas of society can have a massive negative impact. So this kind of multidisciplinary approach that we take to the energy transition seems very daunting. It's technical, it's social, it's political, it's economic. It's very difficult. Now, taking that view from 70 years back, if we also said, but at the same time of realizing that this problem is of its magnitude, you have this tool called a computer, which now has AI capabilities. You explain what I can do. It's like the solution is coming along in parallel with, the most powerful solution tool we have in the history of possibly mankind is coming along at the same time that we have the biggest problem we need to solve as mankind. So it's almost serendipitous in a way. Now, the question is, I think Priya laid them all out. How do we leverage these tools that are available to solve this problem that we have of this magnitude and of its complexity? It is way beyond a single individual or single organization or single entities to unpack this. To even join the dots on a single policy change is incredibly complex. We spend millions of dollars on bringing in experts to unpack what's seemingly a simple question, and it's very difficult. Having machine learning and AI behind us as a supporting tool is huge. I don't think it's anywhere near exploited or used as much as it could be, certainly in the region where I'm working now. I am on a strong learning curve with this, as are the policymakers, as our society. So perhaps a message to funders, as that's what you asked, so first of all, getting behind the energy transition full stop is absolutely critical for obvious reasons I won't go into. But I don't know that there's a huge amount of focus in the specific technologies of AI and driving these technologies as well. There's huge gaps. We at ATB look for gaps where we should operate. This is one space where we're operating because we see a huge gap and a huge need for increased capacity, increased understanding, increased application, increased knowledge transfer and technology transfer.
I think, like, building on that, I do think there's a bit of a fine line, though, because in some sense, climate funding should go to like the goal should be addressing the climate problem. So I think that, of course, like AI and digital technologies are going to be a useful part of that. But then if we swing to the other side of saying, okay, now all of our climate tech funding is specifically only going to the AI part of the solution, when AI is only a part of the solution and there's something broader end to end, it's possible to swing too far in one direction as well. So I think it's important to strike that line between staying focused on the goal and understanding how you kind of support the enablers without kind of over focus on any one enabler, and of course, like, staying focused on the goal. With all that said, I think kind of in the realm of kind of specifically AI as enabler, I would say that the two big funding priorities from my perspective are data and education. So on the data side, how can we kind of create, for example, better mechanisms to share data that is shareable, or create synthetic data where better synthetic data where it's not available, in order to allow more people to come and actually help address the problem. There's a really cool initiative from Linux Foundation Energy called the Open Synth Initiative, which is specifically trying to drive the creation of sharing of synthetic data in the sector to allow more people to come to the table. And there are other initiatives as well, and I'm really excited about those. And then the other is, education. I think that really democratizing expertise on AI and machine learning technologies is really critical to actually allowing these technologies to be used across many different use contexts and actually be scaled up. As we talked about, I think when you are developing these technologies, there are many kind of contextual and domain specific nuances that you have to know about. And so the more people who are able to actually be equipped with the fundamental tools to be able to bring together that domain specific knowledge and the AI knowledge, I think that's really, really important. And it's not just training people in the technical skills to implement AI and machine learning technologies, that's of course super important. But also there's a skill set in terms of how do you evaluate whether something has, worked well, like after it's been deployed, what are your metrics for measuring success, for measuring unintended consequences? How do you do that? Is a skill set in terms of how do you understand the kinds of people and personnel that you need in order to make an AI solution successful. So for example, what is the difference between a data engineer and a data scientist and a software engineer? And do you kind of need these different kinds of people to come to the table? And so I think education, both in the technologies themselves, as well as sort of ethical consideration, impact assessment and measurement, and the kind of capacity you need around these, I think this is like a really important area to invest in.
Thanks, Priya. And I couldn't agree with you more. And some of the other work that we're doing, especially on the last point that you raised around kind of monitoring and evaluation, we're really seeing the need for that. In the Indian context, for an example, we've had about 5-6 years of AI pilots for everything. But now there's really a need to kind of build that evidence base and understand what works, what doesn't, and also to figure out what that monitoring and evaluation actually looks like. AI is obviously not traditional software, so once it encounters new data that is not the training data, there could be many unintended consequences, and all of that obviously requires resources. So I think I'm really glad to hear you kind of call that out, and for that to be something that especially philanthropic capital that has been investing in the AI for social good space. Hopefully they can take that up as an agenda going forward as well. But thank you both so much. I'm so glad that I had this chance to speak with both of you, and I learned a lot, and I'm sure so did our listeners. So thank you both for joining us. Thank you for tuning in to today's episode. We'll be back next month with more conversations at the intersection of climate change and artificial intelligence in Asia. Don't forget to subscribe and do sign up for our monthly newsletter at codegreen.asia. I'm Urvashi Aneja, and on behalf of Digital Futures Lab, thank you for listening.